Hi, good morning. My name's Stephen, and I work at an agency. I help to run an agency called Cruncher in Lausanne. For several years, I was a sound engineer before becoming a front-end engineer. And I've always been really interested in, I've been using Logic and several DAW systems to make music for quite a long time. I've always wanted to program my own, and eventually, at last, we're able to do it inside of the web browser. All the audio processing you just heard was done in Chrome. We're able to do this now. I'm here to talk about writing user interfaces using web audio. User interfaces for me are not just screen user interfaces, but we now have MIDI. As of 4 weeks ago in Chrome 43, Chrome released the Web MIDI API, which means that we have a whole world, we have 30 years worth of MIDI interfaces, including foot pedals, drum pads, keyboards. I don't have a keyboard here. Controller software, mixers. We can control Chrome using a whole load of new devices. How many people here have experimented with the Web Audio API so far? A few of you, okay. Okay, don't worry, I'm going to go through the basics of web audio to begin with. So, the audio processing happens in the browser in a separate thread from the UI processing. JavaScript happens separately from the audio. And what we do is we make calls to the web audio context. There's 3 objects involved in doing web audio stuff. The first one is the audio context. We make calls to the audio context. That creates a processing graph. And a processing graph is like a flow of audio going through the browser. There's nodes in the processing graph. And the third object, so the nodes are the second object. Third object are audio parameters. We make calls to the audio nodes, and we get back audio parameters. Now, an audio processing graph isn't a new idea. The BBC were doing this 60 years ago. You can see, this is Daphne Oram, the inventor of the Oramic synthesizer, one of the early ones. We can see in the background here, she has several filters and oscillators and a couple of tape machines which were actually built by a motorcycle company in Switzerland. And when they chain all these things together, then they would draw graphs that represent how the signal flow through the system went. What I love about this graph is that not all of these components in this graph are mathematical or analog or electronic processes. This component, for example, is an entire room with a loudspeaker and a microphone in it, and they're actually sampling the sound of the room. So, I'm going to go through those 3 objects in a little more detail. You get the audio context from window.audioContext. You create a new audio context, and the most important node is already available to you on the audio context. It's the destination node. It's the most important one, because without it, we won't hear anything. This is where we send all our audio to get it to come out of the loudspeakers. We create our first node. We're going to create a gain node here with methods on the audio context. So here we're doing audio.createGain. It gives us back a gain node. And then every node has a connect method, and we use the connect method to then connect the gain node to the output. I'll go ahead and create a second node. A source node is where we put audio data in order to get it to play back. So we'll create a source node, and we'll connect that to the gain. And that's it. We have an audio graph. I wish it was that simple. The source node, we have to do several things. Each node has its own methods and its own API for putting things into it. So the source node, we have to give it some data for it to play back, which you could get from a WAV file or an AIF or something. That's a separate request. We'll tell it to play back continuously, and then we'll tell it to start playing. So that sets up our first audio graph. Then, in order to control the gain node, I should explain the gain node is a multiplication process. Every signal that goes through a gain node gets multiplied by a value. It's a volume control, essentially, although we're about to see that gain and volume aren't quite the same thing. And we change the value of the multiplication process using the audio parameter, which is called gain. And that's available as a property of the gain node. So an audio parameter has a value, and it also has a number of methods. It's very tempting when we want to change these processes, it's very tempting just to set the value directly. I'm going to show you why you shouldn't do that. I'm going to play back in a minute a sine sweep, and I'm going to set the value halfway through the sine sweep so that we get a change in the gain, a volume change. Let's have a listen to that. There's a nasty click in the middle of that sound, and the nasty click comes from that step change. It's almost, if you can think of your eardrum oscillating with the sine wave, halfway through there, suddenly somebody goes, ugh! Tears your eardrum out. And then we get I'll play that again. We get that nasty click in the middle. What would be better would be a smooth change between one value of the gain and the next. So we're looking for a gain curve. We want the gain curve to be fast enough that we hear it as being immediate, but slow enough that we don't introduce any high-frequency artifacts into the audio signal. And to do that, we use one of the methods of the audio parameter. So in this case, I'm going to use exponential ramp to value at time, which is a bit of a mouthful. And we're going to pass in a value and a time at some point in the future for the curve to arrive at that value. The audio context uses seconds. I know we're used to using milliseconds in JavaScript, but the audio context uses seconds. So I'm taking the current time from the audio context, and I should point out that the audio context uses very, very accurate time. It's even more accurate than the sample rate, which is already very fast. And I'm adding 12 milliseconds on and saying, we'll curve down to this new value in 12 milliseconds. And we get a curve that looks like this. So my first point is, if you're changing values on audio parameters, always use an automation method to set new values, because otherwise you get ugly artifacts. Now that we've done that, we can go ahead and connect up an input. And an ideal kind of input would be a range slider, an input type range. Now, a good audio control has a practical range of values over which you slide. It has a usable law. I'm using audio terminology here. A law is the distribution of values along the range of the slider. It's very rare in audio that we can use linear sliders, because our perception of sound is not linear. And we need a meaningful readout. This is very important for sound engineers. I'm not sure it's quite so important for iTunes or whatnot, but a meaningful readout. Sound engineering is a discipline that's got some similarities to front-end engineering. There's a kind of marriage of aesthetic sensibilities with technical know-how that you find in both disciplines. So let's look at some code. We've got our range slider. It's got minimum and maximum values. And we're doing add event listener. And every time we hear an input event, we're saying, OK, we'll update the gain parameter. We'll say we'll do a curve to the new value over 12 milliseconds in the future. Cool. I've got some examples of that. If I can get this thing to work. Mm-hmm. So, as I said, we're going to change the gain directly. This first button here is the source node that we set up, and then this controls the gain parameter of the gain node. So, I'm going to play some sound now, and just listen to the range of volumes we get as I move the slider up the scale. you'll have noticed that in the first half of the slider, we got a really big increase in volume, and in the second half of the slider, there wasn't so much increase in volume. It's not a very usable range of values. The law, the fader law, isn't correct yet. So let's go ahead and adjust that. The reason for this, yes, the reason is that we're controlling the amplitude of the signal directly, but human ears don't hear amplitude as volume. We hear power as volume. So sure, the audio graph that I started off with, the source node going into the gain node going into the output, is represented here. That represents the source node. It's the play button. The gain node is being controlled by the slider. Can't hear, sorry. This is just an HTML page, yes, with a range input. Yes, sorry, it doesn't look like a standard range input because I've styled it a bit fancy. So I've applied a transform function to make this volume change a lot smoother. And I'll show you what the transform functions are in a minute, but much more usable range of volumes. The same thing is true of other sliders, like a frequency slider. Here in this example, I'm going to filter the audio, and I'm just going to let a little bit of the audio through, just the frequency around about the frequency controlled by this slider. Let's have a listen to this. Most of the range of the slider is taken up with high frequency signal. We've got very little control over the bit we're interested in, the frequencies around speech or around the bass guitar or whatnot. Recently at Cruncher, we bought a new hi-fi, or we were going to buy a new hi-fi, and we had a discussion about who should pay for it. We were going to share the cost of it, and someone suggested that we should only get to listen to the bit that we paid for. So I said to Marco, I said, well, do you want the top end or the bottom end of the frequency spectrum? And he said, oh, I'll have the top end. Of course, I was quite happy with that because he only gets 1 octave, this bit, and I get all of this, which covers the bass guitar and human voice and everything else. So frequency slider also needs a distribution curve. Oh, not playing. To give us a much better, a much more usable range of values. Cool. Just switch back. So let's go over that again. On a volume control, human ears hear power as loudness. Power is proportional to the square of the amplitude. So that's a very easy transform to make. We have a quadratic which simply squares the value coming from their input and then sets that on the... I've missed out a bit of code here, but we get the gain from the square of the value, and then we set it on the gain parameter of the gain node. Yeah, I didn't cover decibels. Frequency control. Human ears hear pitch logarithmically. If you think of a piano keyboard, every octave as it goes up is a doubling of frequency. So that requires a little bit of a more mathematical function, but it's the same idea. We need this transform curve in order to make audio controls consistent with the way we perceive the sound. So my second point is controller values, and not just controller values from screen controls, but controller values from MIDI controls, or for example, when you hit a piano keyboard, you hit it harder. That information about hitting it harder needs to be transformed in some way before being set on audio parameters. So far we've looked at source nodes, gain nodes, we've looked at the destination node. The Web Audio API covers about 20 different nodes, and the ones on the left here are the interesting ones. The ones on the left are the ones that do the mathematical processing to the sound, or the analysis, which lets us visualize the sound. These ones on the right are sound generators and helpers. And there's a few more that I haven't listed here, but they're for doing other things. Great, that's screen controls. But the bit I'm really excited about is MIDI. MIDI stands for Musical Instrument Digital Interface. It was invented in 1983, which is 32 years ago, which means we've got 32 years of musical instruments, interfaces, that we are now able to control Chrome with. MIDI events are really short arrays of information, and they come into Chrome exactly as that, arrays with 3 numbers inside of them. The first number tells you what kind of event this is, and what MIDI channel it's on. There's 16 MIDI channels, and these things are lookable, upable in a map, which is published online. It's easy to search for. And the second 2 are data bytes, and they just tell you information about the MIDI message. So this is a note on channel 1. It's a middle C, and it's fairly loud. And the way we listen to MIDI in the browser is by doing navigator.requestMIDIAccess, which is a promise, returns a promise, which resolves to a value, which I'll call MIDI here. MIDI has several properties, one of which is inputs, another is outputs. We can iterate through those properties, and we can get an input port, and we assign an event handler to the input port, and then we've got all the MIDI information. Now, this in itself isn't particularly useful, because what this function is getting is every single MIDI event possible, including these things are currently sending out MIDI events, just pinging the system saying, I'm here, I'm here. We don't want to listen to those, they're not interesting. So the first job you need to do with MIDI information is to filter it. And I've written a library called MIDI. It's available here at GitHub, sound.io/MIDI. And what it does is it does exactly that. It filters your events. You do MIDI.on, you pass in the values of a MIDI message, and the handle note then is only ever called when that MIDI message comes in. And you can make the filtering as specific as you like. So this will give you every single middle C on MIDI channel 1, and this will give you every single note on MIDI channel 1. You can also pass in an object to you can define the filter with a more human-readable object, which is more useful. So that's the basics of MIDI. We've done the basics of web audio. Let's put the 2 together. This is the graph we set up in the beginning. We've got our source node, our gain node with the gain parameter, and we've got it's all going through to the destination. The input is controlling the gain parameter of the gain node. It'd be really good to get a MIDI controller to do the same thing. This is what we're looking for. Now, when we're controlling the gain with a MIDI controller, it'd be nice if we saw the change on screen at the same time. And to do that, we need to read the values from the Web Audio API and send them back to the range slider. Effectively, we're using the Web Audio API as a model, and we're using each of these components as views which are attached to that model. I'm afraid you can't do this. The Web Audio API doesn't permit this. Let's go back to the original diagram we had. We set up a node graph. By the time we set up a node graph, there's actually no way of inspecting this node graph. The Audio API all runs on a separate thread in the browser. If they made it possible to inspect that thread, then it would interfere with the processing of the audio. So you can't inspect the node graph, nor can you read the values of properties after you've set them with one of the automation methods. The Web Audio API is designed as a write-only API, largely. There's a few provisos to that, but it should be treated as a write-only API. So to model the audio graph, we have to abstract its state somehow. We have to store its state somewhere else. Effectively, we need a model between our views, our view controllers, and the Web Audio API. And the model will be responsible for then controlling the node graph and the values of all the parameters. I've made one, and it's available on sound.io/sound.io. That's the name of the model system that I've used. Sound.io provides a declarative way to set up a web audio graph, an API for changing and observing the graph, and a JSONifiable structure that can be used as a data store. This means, because it's JSONifiable, this means that you can take a patch that you've made in Sound.io, you can install Sound.io on a separate web page, and you can install that patch and you get the same web audio graph back again. Sound.io is, in effect, an audio graph object model, a bit like the DOM object model, but for audio graphs. And this is how you use it. Sound.io is equal to the constructor Sound.io. We pass in a data object. We define all the objects in our graph, and we define the connections between them. We can also define MIDI connections. But if you go to that address, there's some documentation on how to do it. And that sets up the audio graph that we had originally. That sets up our nice little audio, our nice little source node, gain node, destination. Now, Sound.io doesn't just handle single audio nodes in the graph. You can abstract a whole collection of audio nodes, a subgraph of audio nodes, into a single Sound.io object. Here, for example, we've got an input going into a flanger, going into an output. And what's a flanger? Well, a flanger isn't available as a single audio node in the Web Audio API. A flanger, well, we've all seen one of these. Some of us have got them tucked away under our beds still. A flanger is effectively a subgraph of audio nodes. And the four knobs along the top of a flanger pedal are audio parameters that are being exposed to the interface. So we've got a rate parameter of the oscillator. We've got a gain node which controls the depth of the oscillator. We can control the time with another knob, and we can control the feedback. And those things, all of those parameters in Sound.io are exposed on a single object. So for example, we can set the delay time of the flanger, and I've set it here to 200 milliseconds, which is quite long. And that gives us this subgraph of audio nodes. It is basically a plugin system. If you've ever used Cubase or Logic or whatnot, then audio plugins are a big part of that. And this is basically a plugin system for the Web Audio API. So, the web audio graph is effectively write-only. It has to be abstracted if you want to use it in any complex setup with views and controllers. Sound.io abstracts the web audio as a live JSONifiable graph object model. On top of this library, I've built this website. At the beginning of this presentation, I played you some music, and that was using sound.io. I'm going to show you how it works. At least I'm going to try. Let's have a clean setup. So when you first go to sound.io, this is what you see. We've got no, it's all good. Thanks. We've got the input. In fact, I'm just taking the left channel input 1. It's getting routed into a track, and it's going through a gain node, and it's coming out and being sent to the output. And we can see that there's signal coming through. Signal coming through. There we go. And then you can drag effects onto the track simply by... Oh. Okay, the cable rendering's gone wrong. I did a massive refactor of this for this conference, and you might find a few bugs. Each plugin has properties associated with it. So this is a looper. I'm going to just record a short section of sound. SwissJS. SwissJS, 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 SwissJS. Let's send that over there. I'm going to drag some other effects onto it. Okay, you get the idea. Thank you. But that's not all, because each of these controls also has a MIDI button beside it, and if you look along the bottom of the screen there, you can see MIDI information coming into sound.io. So I can train each of these parameters by clicking on the MIDI button to be controllable by a MIDI controller on this thingy. In fact, the most obvious one would be delay to do. Let's do that. So let's take that loop that we've got. MIDI control, it's simple at the moment. I'm going to add things to it over time. I'd be really interested if you wanted to go to Sound.io, to the GitHub repository. I'd be really interested if other people wanted to contribute. And yep, that's Sound.io. Okay, resources. The Web Audio API, that's the address for the Web Audio API. This is a really good resource, the Web Audio Weekly newsletter. It's not actually weekly, but it comes every so often, and it includes lots of really good information about experimental projects. I don't think Sound.io has been featured yet, so you might see it quite soon. I'm Steph Band on Twitter and on GitHub, and Sound.io, this is the repository, and Sound.io's got a Twitter account as well, and this is my little agency in Lausanne. Thank you very much.
So I have a question. What frameworks did you use for this fancy UI? Oh, sorry. Did you hear that?
No, sorry.
So what frameworks did you use for this fancy UI of Sound.io?
I knew someone was going to ask that. I didn't use any frameworks. I wrote a framework. I have a framework on the Cruncher, github.com Cruncher/Sparky, and Sparky is my own templating framework.
Nice.
It does live data binding. It's really cool, and it has scopes.
I have a question. You know, when you're in the shower and you have a hot water bulb and has the range just 1 millimeter, and it's doable for humans and the rest is for aliens, maybe you should design that too.
When you're in the shower, and
Yeah,
sorry, where are you? Oh, you're
yeah.
there. Sorry.
The hot water, the bulb,
Yeah.
has this range of like 1 centimeter.
Yeah, because the usable range is between here and about here. Yeah.
Just this thing.
Yeah, that's a great idea. I think you'll have to ask the Chrome team for that.
Sorry, I'm here. Hi.
Hi.
For your interface, when you hooked up the MIDI device, to recognize the channel, you just... how do you recognize the channels? Did you reprogram it before?
Using that MIDI library that I showed you, I do MIDI.on, and then if you just pass in a function with no filter, it will take every single incoming MIDI message. So once you're listening to every single incoming MIDI message, then you know which thing you've just turned.
Aha, okay, thanks.
I have another question. Do you have a...
Where are you?
Here. In the back row.
Oh, thank you.
Do you have any MIDI producing devices in your application yet, like a step sequencer or something
Nope.
like this? No?
No,
Do you-
the only thing I was using to make sequences there was the looper that's in sound.io.
Okay.
It is something I'd like to look at.
Okay, so there you would accept some contribution, for example.
Absolutely, yeah.
Okay.
I've got a very rough timing system at the moment, but I'd like to write a proper timing system. That would be the first step.
All right. Nice. Very nice library.
Thank you. Well, you haven't seen it yet. You haven't seen the documentation, which is shit.
He will be contributing, so. One more, two more, three more. Do you want to jam some?
Yeah, it's lunchtime now, so if anybody
No.
wants to come and have a little play, then I think we can leave it set up for 20 minutes, is that?
Oh, you can leave it for an hour. So,
An hour then.
and you're
want
not
some lunch.
allowed to eat. You're supposed to play the music. That's why we put you in. So, really no more questions. So, thank you very much first.
Thank you. Cheers.